In the last two videos, we were defining the behavior of the derivative and checking that the sign have a direct implication on how it grows or decays. So we can see if a function is is having increasing behavior or is having a decreasing behavior. And a consequence of that is the fact that when we are around a critical point, then if the function is decreasing before the critical point and then increasing after the critical point, then we have a local minimum. And if the function was increasing before the critical point and decreasing after the critical point, then we have a local maximum. Part 2 has some examples of that, and now we're going to define the theorem. So this theorem is the first derivative test. We're assuming that we have a function that is continuous in an interval that contains a critical point C. And we assume that f is going to be differentiable on that interval. Now, if f prime changes sign from positive to negative as it increases through C, then we have a local maximum. If f prime changes sign from being negative to being positive, then we have a local minimum. If f prime is both positive or negative, then we don't have a local stream at C. Okay? So this summarizes the ideas that we were mentioning before. Now, let's see this with an example again. So we have a function so that the derivative is going to be 12 x plus 1 x minus 1 squared. We had that in part 2, one of the examples, but let's take a look at what happened in that one. So one of the things that you can see is that the critical points are going to be -1 and 1. And when we're checking from minus infinity to -1 and we plug in any number, let's say -2, we're going to get that the derivative is negative. So since the derivative is negative, we have a decreasing behavior by the first derivative test. Then after we move from -1, it turns out that the derivative is positive, both from -1 to 1 and from 1 to infinity. Turns out that if I take any point here, let's say 0, you can see very clearly that this is positive. And notice that although 1 is a critical point, the indication here is that this is not going to be a local streamer, since there is no change in the sign of the derivative. In this case, in -1 though, we do have a local streamer. And in this case, we're changing from being negative in the derivative, which means decreasing behavior, towards an increasing behavior. So we have something that does this. So that's the behavior of a local minimum. Now let's check another function with the derivative. So here we're going to have the function f of x given by the black line, and the purple line is going to represent the derivative. Let's go first to the function. Notice notice the places where we have critical points. Those are the places where we have flat tangent lines for the functions, and so you can identify that we're going to have this in -1 and 1. And as we saw before in this behavior here, there is no really a change in what's happening in 1. In 1, we just have we don't have a local streamer, and we just have a flat behavior going on in here before it continue growing. -1, it is a local minimum though. Okay, and that comes from whatever we were doing here. Now, if we analyze well the signs of the derivative, notice the derivative is negative in all this from -infinity to -1, and that is reflected in the function. The function is decaying, is decreasing. Now, from -1 up to infinity, we can see that the function is always positive, and so the behavior of the derivative, it being always positive, indicates that the function is always going to be growing. And so we see continuous growth from here onwards. Now let's consider another function that has another of the critical points. So the critical points where the function is, where the derivative is not defined. So we're going to have the function so that g prime is 4 minus 5x divided 3x to the 1/3. So this is going to have two critical points, clearly. The one where it's 0, which is 4 over 5, and the one where the derivative is not defined, which is 0. Now, looking on the intervals, we can test with values and from minus infinity to 0, and then from 0 to 4 over 5, and then from 4 over 5 to infinity. We're going to pick some values to test what the signs are. And you're going to notice that in g prime is going to be in minus infinity to 0 is going to be negative, because you're going to have the top being positive and the bottom being negative. From 0 to 4 over 5, you're going to have that this quotient is positive because they're both positive. And from 4 over 5 to infinity, you're going to have that the top is negative and the bottom is positive, giving me a g prime that is negative. So with that, we have that the function is decreasing from minus infinity to 0 and from 4 over 5 to infinity, and it has an increasing interval from 0 to 4 over 5. Now, with that behavior, notice that this is decreasing and then it increases, so we have a potential minimum at 0. Since now it's changing in the 4 over 5, we have a change from increase to decrease, then we have a local maximum at 4 over 5. So now let's take a look at how that looks in terms of the graph. So this function corresponds to this one. And you can see that the function is not existent at 0. Okay. And the derivative. And we have that in 4 over 5. We have that it crosses the axis being 0. Now let's see how it reflects in the function. In the function, indeed, we have a minimum at 0, and we're going to have a local maximum at 4 over 5. Since the derivative does not exist at 0, that's why we have this peak. So you can see that there's very pronounced, and we have a peak here, and then the function smooths out to the local maximum. This reflects the behavior of this function, of the analysis of this function. Now, with this, we can summarize the behavior of this streamer. And we're going to define this theorem here is going to be the one local streamer implies that we have an absolute streamer. So if you suppose that f is continuous in an interval, and that interval contains one local streamer, then if the local maximums occurs at c, then f of c is going to be the absolute maximum of f in that interval. And if the local minimum occur at c, then f of c is the absolute minimum of f on the interval I. Remember, we were always comparing in closed interval these streams sometimes, and the critical points as well. So this is guaranteed that if something is happening in the interior, if we have a critical point, then if that critical point is either a local max or min, then it's going to be the absolute max or min of that interval. So one example of this and why that happens is because when we're close to a local minimum, the graph of the function is not going to bend, let's say it's near to a local minimum, it's not going to bend downward to fall below the value of f of 6. That will create additional local stream values that are not accounted by the fact that this is a critical point. Okay. So around a critical point, if you get that that's a local minimum, then that's going to be the absolute minimum, since there are no chances that the function is going to even go down more. One example of this is consider the function x to the x. This is going to have minimum critical value on the point e to the minus 1. And you can very quickly check between 0 and 2 that this is going to be my local minimum by that theorem. Now, so this is going to be the end of the stream value theorem. Now we're interested in checking what happens with the second derivative. So part 4 is going to check second derivative test, concavity and convexity, and how to complement this to be able to make a full graph.